So in this video, we're going to take a look at driving some old gauges that you can see here. But before you switch off, just stick around for a few minutes because you can use this for a lot of other different applications. It utilizes something called the SignalK Listener. And instead of using an ESP, as we have done in the past, to send data to SignalK, we're going to use an ESP to actually listen to data. So there's lots of other different applications other than driving gauges that you could use that. You could turn something on and off, for example. So just stick around for a little bit and see if this can help solve some of the things that you're having to think about at the moment. So I'm going to run through all the screens that you see here as part of the gauge demonstration. The video really is about that, but what I just wanted to show you very, very quickly, if you're not so interested in that, is the fact that these ESPs can be used as listeners rather than sending data. So in the past, we've always used them as kind of devices with sensors attached to send data to SignalK, but here we're actually listening. So you can see on the screen here, it's going to listen to this path, this electrical battery voltage, and at 12 volts, something's going to happen. So it's going to trigger at that voltage, and we can configure this in the options here. Now, what happens when it goes sort of below that or above, depending on how you want it to trigger, is it will take a pin high or low, and you can change that option here on the screen. And then the pin that it actually changes is set below here. So at the moment, we are going to trigger at 12 volts, the pin to go high or low, depending on what we've set. And the number of the pin is pin number 2. So as I say, the video really is more about driving gauges, but just on the SignalK Listener side, you can configure these paths, you can then listen for values, and then you can take an action on that using an ESP32. And also that is very powerful as well as being able to drive the gauges. Okay, so just before we have a look at the code and how this actually works, let's just talk about these two gauges first and where this kind of come from. We were contacted by a subscriber, and most of the direction of travel for all of us now is to remove gauges like this from our boats because the sensors or the units behind the scenes are getting a little bit long in the tooth, and it's now time to upgrade. We're looking at things like enemy A2000 devices, and those tend not to be compatible with this type of gauge. So this subscriber contacted us and said, I've got a series of these gauges, both at the helm station and below deck, and I'd really like to drive them. I'm going through a similar process as like what we've done, where we started to replace electronics, but actually these gauges still work and they've got some life, and I'd like to drive them. So we thought, yeah, we can try and help with that. So we've got those two gauges there, and then we've also got a more of a traditional resistive type gauge that a lot of boats have, fuel gauge as an example. Now these work in a slightly different way. We were very lucky in that we found some information online about these gauges and how they work. They're all using pulse width modulation, so a very similar way as we drove the LEDs. But for these, we're changing the frequency and keeping the amount of time that signal is high or low, the duty cycle, the same. So the duty cycle for these is set at 80, and to move the gauge, we're changing the frequency. This little fuel gauge that you can see here, this works in a different way. So to get this to work, I had to find a frequency that it was happy working on, and then I changed the duty cycle to make it move up and down. And I'll show you that working in a minute, because I think that has got some good applications as well. So, how does that work? What does all of that mean? Well, we've got 3 different boards here. This first one is a resistive board. So this is the way that I thought about driving this gauge. I just thought that your fuel sender, as an example, sat in the boat, it moves up and down, and as it moves up and down, it changes the resistance. So I'll just buy myself a digital resistor, I'll connect it up to there, and hey presto, it'll work. Well, it didn't. Because of how this works inside, there's actually always some resistance in this, and there's too much resistance in this to drive a gauge like that. So that's out the window. Next, we've got these two devices here, and these are both pulse width modulated MOSFET devices. So what's a MOSFET? Well, it's basically a switch. When this goes on, it lets power through this device. Same with this one, they're both exactly the same. This particular one requires 5 volts to drive it, so an ESP32 can't do that. Maybe a Raspberry Pi could, but again, you might struggle driving it with a Raspberry Pi. So this one's out the window. So that just leaves us with this, and this is the board actually that I've had the most success with. Now these are really cheap, they're on Amazon, they're a couple of quid each. This particular brand is Dollartech, I'll put links in the description. And this board is taking in power, so you take positive and negative power into this board, And then what we do is we send the pulse width modulated signal in on this side. So a PWM to the ESP and a ground to the ESP. And then we turn this on and off at different frequencies and different duty cycles to make these gauges work. So as I say, these gauges here, these work by changing the frequency of that signal, and this one works by changing the duty cycle of that signal. And the code that I've written to go alongside this, which is on the GitHub repository, and you can download it, it will drive 2 of these at the moment with one ESP32. I think we can up that count, but it will drive 2 of them at the moment. It'll listen to 2 different signals, and then it will drive the gauge based on a SignalK path. It will listen to a SignalK path, and then it will output the value. So what do I mean by that? Well, first of all, you have to calibrate these. So you can see the 2 different gauges that we've got here. This one is obviously 0 to 35, and this one is 0 to 12. So I've written the software in a way that you can put different ranges of gauges into that software. So when it came to calibrate this one as an example, I had to calibrate 0, 1, 2, 3, 4, 5, blah, 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 up to 12. When it came to calibrate this one, I had to do 0, 5, 10, 15, 20, 25, 30, and 35. And then when I turned the path on, it was then able to work out what the difference between 0 and 5, and it's pretty accurate, so I'm quite happy with how that's working. So how did I calibrate it? Well, as I say, we were quite lucky in that we got some starting values from this, but it was just basically trial and error. So at first I set the value to 0, then I set it to 5, and then I made the gauge go up to 10, and then I made the gauge go up to 15, and as I was doing that, I was recording that value, and we'll go through this in a minute. And then you put that into a table, you press the button, you tell it to listen to the path, and then you start to send the actual value you want to see. So I don't know whether it's just in shot, it isn't, but at the moment this is receiving a value of about 6.6, 7.8, it's going to go down to 6, 7.7, so it's calibrated against the values that it's going to see. So for this one it's not, and for this one it's actually using meters per second straight out of SignalK. So let's have a quick look at the code and how we will go through the setup procedure next, and then we'll show you the circuit board all drawn out, and we'll get you on your way so that you can do exactly the same and drive all gauges if that's what you want to do. I'm not going to spend a massive amount of time going through the code. I'm going to be completely honest with you, I used a bit of AI to help write this because it got really quite complicated very, very quickly. And as I've said to people in the past, I am not a coder. We've taken a standard kind of ESP template to build this. So what we're doing is we're looking for some values. We're using the SignalK Listener that you can see here. So we're listening to paths in SignalK. And what we're doing then is we're translating that into a curve that we generate as part of that calibration process. So there's 2 curves now that this code will look at. Each one is completely independent of each other. And the paths are also independent of each other. And there's a GUI in a minute, so it's much easier to go through it with the GUI, and that's what we'll look at next. But the code is here. Obviously, you can copy and paste this code. If you know more about this than me, then you know, download it, edit it, make it better, do all of that lovely good stuff. But basically, we are looking at those paths, get the code to set the frequency and the duty cycle. You don't have to change either of them if you don't need to. You can keep one constant as we do with our current gauges, or you can keep the other one constant and change the duty cycle. Or you can change both. It really does not matter. But you do that as part of the calibration process. And then once they're calibrated, the ESP is essentially outputting that PWM signal, and that's all it's doing. And it seems to be able to cope with this really, really easily. I guess it's not a very challenging task for it, to be fair. Here's a second object here, and you can see there's a lot of code, there's a lot of if statements. As I say, I don't know whether the AI's kind of messed this up a little bit, and the proper code is out there. I'll be probably cursing me, but it does work. And as I say, if there are ways to improve it, then please do and let us know. But the code is there, the code is online, download it and use it. So what I'll do now is I want to jump across to the actual web interface because that's more important than anything else. So you can see here it's set to, there's the usual sort of setup in terms of the ESP config about what it's called, its title, how we get to it, all of that lovely good stuff, where everything is, and some of the paths. As it created it, it started calling it Lights Cabin, but we don't really use those terms anymore. They are overwritten in the actual GUI itself. But it's all there, and you can edit it as you see fit. So here's the ESP32. Obviously, you can connect to the ESP either via its IP address, if you know its IP address, or you can use its host name. So as part of the setup process in the code, you can set a host name that you can use to connect to it. And mine is actually dynamic PWM driver. So that is the host name that I would go to, and it should resolve and then sort of connect. But as you can see here at the moment, I'm just connecting to its IP address. So you can see that there are two PWM controllers. You can see the host name, you can see the SSID that we're connected to, the signal strength, the SignalK information. So none of this should be new. If you've done a little bit of ESP work, none of that really should be very new to you. And yeah, you can sort of connect to it and you can understand what's going on. So that's that bit of it. There's the name that you can change so that you can get to it more easily than going to or trying to find out its IP address. You can turn on the authentication, you can restart it, or you can reset it to your factory defaults. Next, you've got your Wi-Fi set up. So this is how you would set it up and connect it to your SignalK instance. Again, all sort of normal stuff, nothing sort of out of the ordinary there. On the SignalK configuration, you can see the SignalK that mine's just called openplotter.local, or you can put its IP address. That's how it discovers it. And then it will connect. And then finally, we've got the configuration. So here you can see a number of different paths that are set up as part of this. So we can actually manually configure the values for both duty cycle and frequency on this page to try and calibrate it, but there's far easier ways than doing that. And that's why I've included these paths, because that's the easiest way to do it basically. So these two are the duty cycle and the frequency path for PWM controller number 1. And this is the path that it's going to listen to. So instrument 1 listen path, that's what it's actually listening to. This bit of configuration in here is how we calibrate. So you can see here that when the value of 0 comes in, the value that it outputs for duty cycle on this is 0. When the value of 1 comes in, the output is 80. And the maximum for that speed gauge is 12 knots, so that's 12. And at 12 knots, I found actually just upping the PWM ever so slightly to 83 helps a little bit to get the gauge to go to 12. So between 1 and 12, the duty cycle will be between 80 and 83. So as it goes up, it will slowly increase that up to a maximum of 83. Now, the frequency on this is listed below, and it's doing exactly the same. So at the value of 0, the frequency will be 7. At the value of 1, the frequency will be 9, 2, 18, 3, 28, and so on and so forth, and it goes all the way up. So again, this creates like this scaling that it's going to use of how it's going to translate a value that we send it, in this case, speed of knots from 0 to 12, to an output that the PWM controller can send out, which ultimately drives the gauge. So that's how it works. So you gather these values by going through and setting it up first, and then once you're happy with it, you put the values in here and you turn on use curve. Once you turn on use curve, you can no longer manually set the values. It then is listening to this path. If you turn this back off, it'll listen to these paths again, and you can set whatever you want with sliders or however node red or however you want to do it. But when you finish calibrating and you want it to use this and you want it to listen to the path, you check this option here and you hit save. Now below is exactly the same. You can see here, now this one actually works fine on 83. So this one, the duty cycle of 83 between 1 and 35. So remember, this now is the knots gauge. So the values that this is expected to see, sorry, it's in meters per second actually. So the values that this is expected to see is between 1 and 35 meters per second. And that's what the gauge will display. So this is the calibration that happened to get these gauges to work. So you can see here 15 meters per second was 52, 20 was 69, 25 was 85. And then once you turn this on and you hit save and you set your path, it then starts to work. So how do we calibrate? So let's go through the calibration process. So what we've done now is we've turned off the use curve on both of them, and we've hit save and we've pressed restart, so that the device is restarting now and the gauges have come back up. And you can see here there's a little bit of something here on this one. This one's just popped up a little bit. So you've got these paths here, and what I've done is I've created a little node-RED sketch. And all this does is this just creates the path in SignalK so that I can use something like KIP to very quickly use the sliders, put the sliders together and use the sliders to actually send some values out to the gauges. So here you can see that in action. We've got the duty cycle and the frequency for the first one, and we just basically send a 0 and a 7 out of that first, and that then creates the path in SignalK. Just ignore the bottom bit, ignore this section here. This is just another way for us to very quickly check that we can get through to 1 to 12, and I've done the same for the second one. I will also put this code, this sketch online so that you can copy it, but we have done this before. We did this as part of the digital switching bit where we created paths that we could then interact with, and that's exactly what I'm doing. Same thing here. And then this is how we sort of test 0 to 35, but we'll come back to that in a second. So once we've done that, that then creates us these paths that we can then interact with something else. And the easiest way for us to do that, or one of the easiest ways that I think, is using KIP. So now I've got my KIP set up here, and I've got duty cycle and frequency for both PWM controller 1 and PWM controller 2. So gauge 1, gauge 2. So if I then apply, because we know some of these values anyway, so I'm going to apply 80 to that, or 81 will do, and then I start to bring, you can already see actually it's moved up a little bit. I start to apply some frequencies to this. You can see that the value is starting to go up, and this is how I set it. So I just carried on moving this value until I got it to where I wanted it. So almost at 6 there. Let's get it to 6. Bit of fine tuning. Oh, gone past it. So you just play about with this until you get the value that you want, so that it displays the value on the gauge, and then you use that value as part of your calibration process. So if we drop it back down again, pick another value. So we're almost at 4 there. So we'll pick a value that takes us to 4, there we go. So that would be 4, and I would write that value down. Let's do this one. So we'll bring the duty cycle up on this one. Okay, so it's just come off the bottom there, and we do exactly the same process. We'd start picking values until we got 5, 10, just go up the gauge. We keep going up and up and up until we found the values that we wanted, and we just write those down. And that's what you saw on this screen here. These are the values that you saw. So once that's done, we'll drop these back to 0, or as low as we possibly can. And the gauges should go off, and they have. We then turn on these. So we then go back through and we'll hit save on that one, save on that one. We'll hit restart. Hopefully you'll now see the little needle test bounce. There it goes. And then it'll come back down, and it'll go to the values that we then send to them. So now, of course, it's now listening to a path. So I've configured the path here. So at the bottom, so if I set a speed of 3, we get 3. If I set a wind speed of, what's that value? 16, we get 16. Why isn't that moving? Let's just fix that. It's not moving there. Ah, that's wrong. Let's just change that to 2. There we go, 16, and I'm getting 16 on the gauge. So if I carry on messing about with these, you'll see them move all over the place. The speed will come up. We can bounce around all over the place with this. Bring them back down. That's it. That's exactly how it works. So you can see a little bit, I've got a little bit of misconfiguration here. Look, that's almost 3.5, and actually I've got 3 on the screen. So you do have to mess about with them. It's not, you know, you're going to have to find the value that you want, and you can continue to calibrate them as part of that process. And then once you're ready, you press save. So that's how that bit works. So how do you then connect them to the path? Well, you've got a couple of different options. You can come back over here and you can literally change that to the path value in SignalK. So if I wanted to listen to the speed, then I could change that to be speed through the water or speed over the ground, whatever I wanted. The other option is that you could go into Node Red, and that's where you can see a little bit of extra configuration here. I was just using test data, but again, I could set it up so that in Node Red, that's how I deliver it to the path if I really wanted to. Don't have to, I just set that up to mess about with the gauges really, but that's essentially what you do. You then change this across, you hit save, and it will start listening, as you saw earlier in the demo where they were bouncing around and they were listening to values that were coming out of SignalK, and that's it, and that's how you drive the gauges. Okay, so finally we'll move on to the fuel gauge. So as I said before, these two work in a slightly different way. This one wants a frequency change in order to move the gauge, where this one wants a duty cycle change in order to make the gauge move. So this is a standard sort of fuel gauge that you would see on a boat, and I think this has got quite a lot of different applications because, again, these are very simple and very cheap. So a lot of us have these, and a lot of us have a resistive fuel gauge sender. So as the fuel drops in the tank or increases, that resistance changes, and then therefore that moves the gauge. We'll just turn it off. So as you can see, it goes off, and as we turn it back on, it instantly jumps to full. And there it goes. So how it works is, as we change the resistance on the sensor wire, then it would therefore move the gauge. But here what we're doing is we're doing the same thing, but we're using the PWM controller that you can see at the back, and that's what that yellow wire is. We'll go through the wiring in a little bit, but basically we are earthing this out at different amounts to trick it in thinking it's seen a resistance and then move the gauge. So if we move over to the config, here's the config. You've seen this before, but obviously we're going to use different values in here. So in order to control this, I've turned this off again. So now we can send values. And then we jump over to KIP. Now, this is a bit more trial and error than the other one because I had to find a frequency that it would use. And you can see there, I'm sending it across at 4,000 hertz. And that seems to be the frequency that the gauge moves the most on. So if I just do a bit of a demo and I drop this right down, you'll actually see that it hardly moves. It doesn't respond at all. It'll respond if I earth it out completely. There we go. And if I take that away, it will then eventually respond and go back to full. But I have no control over any of the other values. It just doesn't want to respond. And I've tried different frequencies in order to make it work. And actually 4,000 seems to be the best. So if I just... And again, this was all trial and error, so if I move it up a little bit, it still doesn't want to respond unless we get like up very, very high up to the top where basically we're earthing it out. And then all of a sudden, as I kept moving this up, I started to get just a little bit of response from it. It's not going to do it yet. There we go. So I've got some sort of control there, but I haven't got very much range. I've either got like less than quarter of a tank or full. It just doesn't want to respond. I can make it go to empty, but I can't control kind of the top, so I can't, nothing down here works. Just goes straight to full. And then as I say, as I started to play with it more, I got this frequency right up to about 4,000, and then it did start getting some control over it. So, okay. So it's very hard to get that top rating to work, and again, you just have to play about with the figures a little bit until you get it to move. But it is starting to move now. Hopefully you can see the gauge. Now we're at a quarter of a tank. We're starting to come up now. Half a tank. Coming up for 3/4 of a tank. There's 3/4 of a tank. Just over 3/4 of a tank. And then in a second it'll jump to full. So that top bit, even now, again, like I say, you'd probably have to play about a little bit more to get more accuracy here. It may be that your gauge, I know on our boat, that top bit, it doesn't seem to move, and then all of a sudden we go from full to to kind of 3/4. This bit of the gauge is actually more of my gauge on my boat. The half a tank actually represents more like 3/4, and it's broken out more. So if I got that sort of finer control, then I could move that. But again, you'd have to make sure that the readings that you're currently getting, you'd have to make sure that the sender then married up to you driving the gauge in this way. We can drive different gauges, basically. We can drive this type of gauge, and we can drive gauges that need a frequency change rather than a duty cycle change. So I think it's got a lot of different applications. So how is it all wired up? So we'll just move to see behind the gauge, and you can see. So we've got positive and negative coming in. So excuse the bolts, I couldn't find anything else to wire this together with, but we've got positive and negative, and we're taking a positive and a negative to the gauge. So that's normal to power the gauge. And then what we also have to do is we have to take positive and negative to the board as well. So you can see there is a red and a black wire here going over to this, and that's to actually drive the circuitry. On this side of the board, this is where you're connecting up to your ESP, and as I say, you've got a ground and a pulse width signal coming in, and then this little bit of circuitry in the middle here, this is an octacoupler. So what that does is it uses light. So it has a diode, an LED diode in it, and a receiver, and it creates isolation between these two sides. So this side is operating on like 3.5 volts, 3 volts, and this side can operate on a lot of different voltage. It doesn't really matter. And that's the beauty of these little boards. And then you've got a switch in the middle there, and that is turning that switch on and off very, very quickly. So this yellow wire is essentially connected to the negative. So when we put this on maximum, what it's doing then is really, it's just earthing out this gauge. So this gauge then, the yellow wire is connected to the negative, and the gauge is earthed, and that then moves the gauge to one side. And when we go up the scale, we're then varying the amounts of earth we see on this cable. Essentially, we're kind of tapping this very, very quickly, and that's what it's doing. So here you can see we've got the circuit diagram drawn out. We've got the gauge, we've got the signal wire, it's 12 volt supply, it's negative supply. At the bottom we've got the dollar tech unit. You can see it's negative and PWM signal, and then it outputs that signal to the gauge. And you can see the ESP above with its power supply as well. So I hope that's been useful. It was certainly an interesting project to work on. If you've got any questions or comments, stick them in the comment section below or drop us an email, and we'll see you next time.